It works. Seems to work. Okay. Thank you very much. I'm really grateful to be here. I think you pronounced my name really well, but just to keep reminding you, it's Mirjam Blokker. I work with KWR, and I thought it would be nice to just quickly introduce what KWR actually is. So in 1948, I think there were about 150 water companies in the Netherlands, and they decided to team up. And they started KIWA, which was really about certification of water-related articles, it was back then. And then in 1971, they also decided to set up a joint research program. So that was where KWR was originally from. It was then founded. And in 2006, KIWA let us go. So we split, and now it's just KWR. So originally, we were KIWA Water Research, but we're not allowed to use that name anymore. So we're really KWR. We now have 10 drinking water companies. They're still in the joint research program, and we're so successful that even one from Belgium has joined us as well. So they're our shareholders, and they're primary customers as well. We're in this really great building since about 4 years, very transparent, a lot of places where you can meet colleagues from all different teams. So I'm down here talking to one of my colleagues from the microbiology group. So there's lots of interactions with all the different aspects of drinking water and wastewater as well. I wanted to tell you a little bit about how drinking water is distributed in the Netherlands and some of its peculiarities, and why we have the best drinking water in the world. We have a network of 120,000 kilometers of pipes. Today, that's about 50% plastic pipes, 30% is asbestos cement pipes, that's decreasing, and there's still about 10% of cast iron pipes, that usually the older pipes. About 3%, 5% leakage, quite low. The replacement rate is quite low as well. It's 0.5% per year, but it is increasing. So to about 1%, so maybe the pipes will be 100 years old when they're replaced on average. Average pipe age, I didn't put it on, but it's about 45 to 50 years right now. And the research questions now are much more on how do we maintain this network. So in the past, it was built, and it was much more on how do we build it, where do we get the money for building new networks, but now it's much more about keeping the best quality that we have. So which pipes need replacement, and when do you replace it, and what do you replace them with? So this is really a view of the Dutch utilities, is when we replace a pipe, we don't just replace it with the same pipe, but we actually use it as an opportunity to improve our network even further, and really have a future-proof network. And of course, we also see lots of busy urban environments where you have many other players in the underground, and you have to work with them as well. It's also quite a challenge. So some of the typical things for Dutch drinking water distribution, and I've put them into practice, so what's been going on for years and years and years, and then in the second column will be what did research add to that, and then a third column on what sort of research do we still do. I think one of the aspects that is really important is that there's been a focus on quality and long term. So it's not this cheap, quick fix solution, it's always a future view of and quality view. I think also quite important, the fee that we pay for drinking water, about €2 per cubic meter, really covers all costs, so there's no subsidies from the government. Water utilities are led like a company, but they are actually in public hands, so their shareholders are municipalities and provinces. There's no residual chlorine in the system. There's a low leakage, low burst rate, and also quite a low number of customer complaints on water quality in general, but specifically discoloration is quite a low number compared worldwide. Then what is going on right now, so the last 10 years, you can see that they really put a lot of the research results into practice. So one of the things is network design. It's not just put in big pipes, have plumbing expertise and add safety factor to safety factor, but really have a research-based vision on what a proper design of a system is and actually build that. Also network operations, we're looking much more on data that we've collected on valves, on hydrants, and use that for asset management, and the same for network replacement, where we incorporate data from failure registration database, a national registration database, inspection techniques, models, and insight into pipe degradation, pipe material degradation. And then I'll discuss a little bit about some of these topics, not all of them, I don't have the time. And the current research is much focused on asset management, also on water quality, demand modeling, and hydraulics modeling, and water quality modeling. As we do not use chlorine, we need biostable water. We need to make sure there's no contaminations or as little as possible, and do quantitative microbial risk analysis to keep that low. And of course, sensors and sensor interpretation is very important research topic nowadays. So a little bit on the practice. I put in 2, but I think I'll talk more about the leakage than the residual chlorine. So if you get the slides, you can read this, and there's a paper that connected to that. But the low leakage, 3 to 5%, and we didn't really bring it down, it always was this low. How did we do that? So in 2004, we did a project with UK companies that really didn't believe us when we said it was 3%. So they said suspiciously low, and we challenged them to find out how and why, if it was really true. So we used both our methods of top-down and bottom-up estimation of non-revenue water on a UK side and a Dutch side, compared them, and actually they seem to be lead to the same result. And we also did some exploration in the field in the Netherlands, tried to find leaks. And we didn't go to a place where we thought, oh, this is the best place. We went to somewhere where we thought there might be some leaks there, but we didn't really find them. But they did come up with some explanations of why leakage is low. And instead of suspiciously low, they now say, okay, we believe you. And it was confirmed, but still maybe ridiculously low. So some of this is the different colors, and I'm not really sure exactly what it meant, but some of this is related to the lucky circumstances that we have. So there's low pressure because it's such a flat country. The soil is very primitive. When there is a leak, water will just come up to the surface, and you can quickly find it and repair it. The age of the network is not that high, low pressures, or things like that. But there's also some good engineering practice that we found. And the best quote that I have is that somebody from the UK said, I wish that my engineers in the field would speak as good English as yours do, and ours are Dutch people. So it was quite interesting to see that education and everybody who works on a pipe really knows I'm working on public health good. It's water quality is very important. So it helps, and it does lead to low leakage because there's a connection for every household pipe and not everything plugged together, for example. So it's really good engineering practice there as well. Now a little bit on the design of a system, and the self-cleaning networks is something that is really very typically Dutch. All Dutch water utilities have implemented it. Some piloting is going on in Belgium, and hopefully next year or this year in the UK. But it's a really good story, I believe. I really like to tell. So there is discoloration, not very often, but once in a while you fill up a bath and you can see it, and you can make a photograph. I've never seen it myself like this, but everybody knows it's at some point in your life you've seen this. Story in the whole world is it's from corroded pipes, right? That's the reason why you have this, and there's nothing you can do about it. But really, as I said in the beginning, there's only 10% cast iron pipes in our network. Can't really be just that. Besides, they're coated, coal tar bitumen coatings, most of them still intact, so it's not a lot of corroded pipes there. So this was the first it was a hypothesis. It must come from the treatment, there's particles coming in, and eventually something happens in between during transport and distribution leading to this. Now, it's not just a hypothesis, it's been extensively tested, and this is really what the true story is. But you can also do something with that knowledge. So what it is there's particles coming in from the treatment, just a few, but it's days by days, months, years of loading the system. They will, in the system of hundreds of kilometers, just deposit. And every now and then when you would open a hydrant, you get a hydraulic event, and then it's resuspended, and that leads to discolored water. So if you make sure that what goes in goes out, then you won't have this problem. And this is typically what all water utilities do, because they flush every 3 years, 5 years, 10 years, I don't know exactly. But the trick for the self-cleaning systems is that this balancing happens every day or every other day. So everything that settles during the night is resuspended during the morning peak. And it's really very small amounts, so you'll have the self-cleaning system. And that basically leads to discolored water in the normal system and a really self-cleaning system in the new design, where your disturbance, if you open a hydrant, is basically the same as what happens every day during your morning peak. So how do you do this? You make sure that there are no locations where there's anything that can settle. So there's no flow direction reversals. It's a branch system. Velocity is high enough during the morning peak, so small pipe diameters. In the Dutch system with the demands we have, that means 110, 63, 40 millimeter pipes. And it might be a little bit larger here. Of course, don't use corroding pipe material, and you will see that still once every year when you have a really high demand, you still have enough head available to deliver all the water. And this is what that looks like in practice. So here's your very safe, secure, looped system, 250 millimeters and higher. That is the backbone, and then you branch off to 110. This here is not connected, and then it goes to 63, 40 millimeter pipes. And this is about 150 homes that are connected like that. There's still hydrants. We build, the Bavin build a special hydrant that would fit onto a 63 millimeter pipe. This can still deliver 30 cubic meters per hour of firefighting capacity. And then after this, it will go directly into the home. This means that there's no dead end, it's a flowing end. So there's no dead ends in that system. Now I want to talk to you a little bit about the research that we're doing. And the example is for asbestos cement pipes, but we do similar research on PVC pipes and other pipe materials. So what we've done in the past, and I could almost have, well, I could have added a new figure to this. I'll talk to that. That relates actually to something that Mohammed just said. But so we look at pipe degradation mechanisms. So we really look at the science behind the degradation. Then we try to combine that with the failure registration data that we have. There's a slide next to this. And we also look at exit assessment on leaching, for example, here to see with the pH test what the strength of the wall still is. And you can even correlate that with inspection with georadar, echo pulse, ultrasound. And the graph that next time I'll put here is a CT scan, because we actually put AC pipes into a CT scanner. You said you wanted to have the full image of your system. Well, of course you have to excavate it and then put it in the MRI or the CT scanner, but we have a really nice view of what that pipe actually looks like. So this gives us really a lot of insight of how AC pipes degrade over time, and this will help for the utilities to estimate when to replace which pipe and really do this in a cost-optimal way. The failure registration database that we have, and this slide is from October 2016, sorry, but back then we had 18,000 bursts registered, so there's more than 20,000 now. 8 of the drinking water companies are contributing since about 5, 6, 7 years. And this was under development. The quality system is now in place. So the data quality is guaranteed. There's a system of how good the data quality is, what's put in. And the Belgium company is still joining, I guess. And what we can see here, for example, is failure frequency of AC pipes in purple, and then the number of failures that were registered. And you can either look at it per age group or per installation date, which might also be important. You can also see how different soil types around the pipes would affect it. So there's more corrosive soil types that would affect aging of AC pipes. This graph here shows for different installation times for one of the water companies the number of failures in PVC in the pipes in the darker color, and the lighter color is the PVC joints. So we can also compare those. So this is a really treasure of data, and it's still growing. And as I showed before, failure rate is quite low, but water utilities teaming up, collecting all the data together, really give them a lot of insight, not just on their own pipes, but for the whole of the Netherlands, and collect a lot more insight a lot quicker than they would with just their own data. So I told you a little bit about how water utilities work in the Netherlands, their view on quality, their view on research. They contribute, they invest in that, they actually use it, and more research is still being done together with them in the joint research program. And this really leads to water that looks good, is clear, that tastes good, there's no chlorine, people drink from the tap really. It's always available, more or less, and it's not expensive at all. So with that, I really like to thank you for your attention.